Hi, welcome to Physics 1402. This is our first lecture on electrostatic charges and methods of charging. So these lectures are designed to introduce you to concepts and get you started on how to use the equations and concepts to solve problems. So when we're talking about electric charge, charge comes from subatomic particles. Now, when you dig really deep into it, the surface that we're talking about here is not really what's going on. We're working kind of on an introductory level, so we're just going to assume that the smallest part of charge are going to be the positive protons and the negative electrons, and then the neutrons don't have a charge. Now, when we come down to later in the semester, when we start talking about modern physics, we learn that actually charge comes from smaller quantities that are actually located within the subatomic particles. And we'll get to that later, okay? But for now, we're just going to think about what you knew about charge from maybe chemistry in high school. So, like charges are going to repel, opposite charges attract. And our charges are going to be either static or dynamic. When we speak of dynamic charges, what we're really thinking about mostly are like currents. So you're going to have like your electric circuits. So we're going to start with electrostatics at the beginning here. So when you think about charge, the symbol for charge is generally going to be a lowercase q, although sometimes we use a capital Q. But that lowercase q, we use lowercase letters generally to represent values that can change. Q is sometimes, in capital terms, used to refer to a very specific amount of charge. The unit is the coulomb, which is a capital C. And when we look at charge, since we're assuming our charges come from protons and electrons, we sometimes use the lowercase letter e to represent an elementary charge, which is either a proton or an electron. And so when we look here, this value 1.6 times 10 to the negative 19th coulombs, this is the value of E, and that's a lowercase e. And that value is provided for you on your formula sheet, so you don't have to memorize it. It is a very, very, very small value. So a proton or electron has a very, very tiny amount of charge. Now, the electrons have negative charges. The protons have positive charges. So they have the same magnitude of charge, but opposite signs. Now, the neutron itself has no charge. Not because there aren't any charges in the neutron. There are actually both positive and negative charges located within a neutron. When you think about nuclear physics, we'll see that a neutron is almost like a proton with kind of like an electron stuck on it. That's kind of what a neutron is, which is why when you look at the mass of the proton and the mass of the neutron are the same to three significant figures. When you break it down to more decimals, you'll see that the neutron has a tiny bit larger charge, and that is due to the fact that it's got this extra negative charge added onto it. Now, the electron has a very, very, very tiny amount of mass, I apologize, has a very, very small mass compared to the proton and the electron, because the proton are times 10 to the negative 27th kilograms for the neutron, and our electron is times 10 to the negative 31st kilograms, so significantly smaller. So we discovered the charge of the electron using an experiment called Millikan's oil drop experiment. And what Millikan did is he took an atomizer, which is kind of like a perfume sprayer, and it creates a very, very fine mist, and it made a very, very fine mist of oil droplets. And these oil droplets were negatively charged. So what would happen is gravity would pull the oil droplets down. But there was a positively charged plate and a negatively charged plate. And so what would happen if you picture about what's going on, the electrons would be attracted to the positive plate while gravity is pulling them down. And this ionizing radiation would excite the electrons and cause them to jump up and down, making the oil droplets kind of glow so that they're visible to the scientist who's observing them through like this telescope, basically. The fact that they're also oil droplets means there's an additional force of viscosity going on. That force of viscosity is kind of like the drag force that you might have encountered in Physics 1401. And so that is always in the opposite direction of the motion. So as the droplets are trying to fall, because gravity's pulling them down, the electric field would be pulling up and attracting the electron to the positive charges. At the same time, the drag force is also working in the opposite direction. And so what Millikan was able to do is he was able to adjust the power source that was charging the plates until the droplet would stop. And it would stop in air. And so therefore it would be in equilibrium. So the net force would be 0 for the drop to be stationary. So these three forces, QE, we're going to find is our electric force based on a charge Q. And then our gravitational force mg and BV, that is the drag force, would all be equal. And so since we found the point where it was stationary, the velocity became 0. So the drag force disappeared. So QE was equal to mg. Now, each of these droplets actually had different masses, because some drops were only missing 1 electron, some were missing more electrons, and so the mass would change, and so would Q. E is the strength of the electric field created by the plates, so that was a known value. G is our acceleration due to gravity. It was also a known value. And essentially what he found is he found that no matter what the mass was, the charge that was needed in what they found, that charge was always a multiple of that 1.6 times 10 to the negative 19th coulombs. So that is how we figured out that that had to be the charge of an electron. We also called that quantized because it's a quantum. It's like a fixed value that it's being multiplied by. So that was kind of cool, that as the mass increased, the charge increased, and there was some proportionality to it, and that was based on that charge of 1 electron. So this is how we found out that our charge of an electron is 1.6 times 10 to the negative 19 coulombs. That coulomb is our SI unit of charge, capital C. And when we say quantize, as I mentioned, that means that charge is always going to be a multiple of E. So charge Q is going to be N times E, where E is our 1.6 times 10 to the negative 19 coulombs. And N is going to be some sort of integer value. So 1 electron, 2 electrons, Avogadro's number of electrons. It doesn't matter what N is, but it's going to be an integer value. You cannot have a partial charge. And then we can just define the net charge to be the charge of like a whole object. So an object is going to have either more protons or more electrons, and that is going to be that net charge. When we talk about Q, that lowercase q, we're really talking about the net charge, unless we're talking about n individual proton or n individual electron. There is also, therefore, the law of conservation of charge, and that is that the net charge of an isolated system remains constant. So, for example, charge can be transferred between different objects. If you take a balloon and rub it against another balloon, you can get those balloons to kind of get charged up, and you can then get all cool different things to happen. So charge can be transferred between objects, but the total charge has to be the same. So this idea of conservation of charge means that the charge cannot be created or destroyed. So for example, if I start off with 2 objects, one with a positive 4 charge and another with a negative 12 charge, my total charge at the start is negative 8. So then what happens if I take those 2 objects and I touch them together? If they're conductors, those charges are going to be free to move around. And what's going to happen is the charges are going to rearrange themselves until the charges are equal on both objects, as long as the objects are identical in size. We'll see later that if the objects are different sizes, the charges will redistribute themselves, but not always equally. So since I had -8's worth of charge at the start, when I separate these equally sized conductors, I'm also going to have a total of -8 at the end. If they're equal sized objects, that means they're both going to have a -4 worth of charge. Now that could be coulombs, microcoulombs, it doesn't really say. But the total amount of charge has to stay the same. They're just going to rearrange themselves. Now, how they rearrange themselves and the ease with which they do that is going to be based on whether they're a conductor or an insulator. So conductors are materials that allow charge to move readily through it. So that would be something like a metal. Your insulators are going to restrict the movement of the charge. So that'd be something that is going to kind of prevent the charges from flowing. So for example, plastic, rubber, things like that. So for example, wire is made out of a conductor, which is the copper inside, and then the insulator on the outside is usually some sort of plastic that prevents the charges from escaping from the wire. So that way electricity can flow freely into your house without you being at risk of being electrically shocked. Now, there's no such thing as a true conductor where it's has absolutely no resistance. There isn't really anything that is also a pure insulator and completely perfectly resists the flow of charge. It's more like a spectrum. So our conductors are going to be materials that are going to have more of a tendency to allow the electrons to move. They're going to be metals, and the reason they're metals is the valence electrons of metals are loosely bound. If you've had chemistry, they're going to have a dense kind of core in the center of electrons, and that kind of shields the protons from being able to reach the electrons that are way out on the outside. So those electrons in the valence on the outside of the atom are easily free to move around. Our insulators are going to be poor conductors. They are going to be materials that have electrons that are tightly bound, and so the electrons are not free to move. So those are going to be things like glass, rubber, plastic that we have. So you can kind of see that it's still a spectrum. So like silver is a very, very, very good conductor. But carbon is also going to be a conductor, just not as good as silver. Now copper is a better conductor than, say, iron, but actually not as good a conductor as silver. When we get to insulators, the insulator, something like rubber, is a very good insulator. So that's why we tend to use that around electrical equipment and so forth. It's also going to be something that's readily, easily for us to make. And then in the middle are going to be our semiconductors. So the semiconductors are going to be those materials that are kind of in between our conductors and insulators. And they're going to be really good for electronics because by manipulating how much of the semiconductor is there, they can control the flow of electricity. They also don't tend to conduct heat as well, so therefore they're not going to heat up or cool down quite as fast as maybe some of the conductors will, which makes them really good in different circumstances. Now, how do objects become charged? So atoms are basically neutral. They have the same number of protons and electrons. It is possible to transfer electrons away. And there's three things that we can do. We can do that by friction, conduction, or induction. What's really, really, really important is no matter what happens to our total charge, whether it becomes positive or negative, only the electrons can move. The protons and the neutrons are stuck within the atom in that nucleus, and they are held and bound in the nucleus. The electrons are on the outside of the atom, and actually when you think about the size of a nucleus compared to the size of the whole atom, I mean, there's actually a huge separation distance between this, where the nucleus is located and where those outer electrons are. So only electrons can move. So if an object becomes positively charged, it's because they've lost an electron. If it becomes negatively charged, it's because they've gained electrons. The protons never move. So starting with friction, so what happens with friction is that insulators themselves can be rubbed against each other. So charging by friction is going to work for insulators. And what's going to happen is one object becomes negatively charged and the other object becomes positively charged, and they have to acquire equal but opposite charges. And that's because of conservation of charge. So, for example, rubbing a rubber rod with fur will transfer electrons from the fur to the rubber. And that leaves the rubber rod with a net negative charge. This can also happen accidentally. For example, if you are walking across a carpet, you tend to get zapped. And that's going to happen because the carpet is going to transfer electrons to your shoes. Those electrons are going to move up around your body, and they're going to have a chance to transfer into the doorknob itself. I just like this. This is kind of fun about Smashbox Mascara trying to use science to kind of justify why their mascara is so good. And they're using this idea of charging by friction is going to attract the negative into the positive charges so that the mascara stays on your eyelashes. I think that's fun. All right, so charging by friction. So how do we know which objects become positive or negative? Well, it's going to come back down to kind of what you studied in chemistry. So electron affinity is a measure of an atom's ability to attract electrons to it. So every atom, every molecule has a different electron affinity. So the objects on this list is called a triboelectric series. And the objects that are up here towards the top are objects that tend to become positively charged. The objects down at the bottom tend to become negatively charged. So these are going to be your objects here that tend to gain electrons, where these ones up here tend to lose the electrons to become positive. So how do you know which object is become negative or positive? Well, you look on the list. Basically, the lower down on the list it is, the more likely it's going to become negatively charged. So if I take rubber and I rub it against polyester, okay, a lot of your clothes might be made of polyester, then what's going to happen is the rubber is going to tend to become negatively charged, and the polyester is going to tend to become positively charged. But if I take that same polyester and I rub it against the wool, what's going to happen is, even though these are both on the top half of this, the wool is higher. So the wool's going to tend to become positively charged, and the polyester is going to tend to become negatively charged. And because of conservation of charge, this is going to have to be an equal and opposite amount of charge. So we can see this with a little demonstration. All right, so here we have a rubber balloon and a wool sweater. So the rubber balloon, I can kind of rub over here on the sweater, and then I can see that it's now attracted to the sweater. So what is going on? So if I reset this and I show all of the charges, so basically our sweater starts off neutral with equal numbers of positive and negative charges. Our rubber balloon also starts off neutral, as does our wall over here. So what happens is, if I take the rubber balloon and I rub it on the sweater, what happens is the rubber balloon has a higher electron affinity, and so it's going to attract the electrons away from the wool. This leaves the wool with a net positive charge and my balloon with a net negative charge. And now the opposites attract. That is charging by friction. Now, our next method is charging by conduction. So conduction requires conductive substances, so generally metals. And you need to have one object starting with a charge. Now, I will give you a little warning with these images. A lot of times when you're looking at physics diagrams, they don't show the total charges, they show the net charges. So, for example, this rod right here is positively charged, not because it only has positive charges. It has both positive and negative charges, but it has an excess number of positive charges. So somewhere along the way, it's lost electrons. So it's not showing all of the charges, just the ones that are extra, just the extra positives. Now we have a neutral metal sphere over here. So what's going to happen is if you bring the rod next to it, the positively charged rod, there are going to be electrons, and the electrons in both objects are going to be repelling each other. At the same time, the positives are attracting the negatives. Well, what happens is that these negative charges are going to be held in place by an equal number of positive charges because it's neutral. But there's this high density of positive charges further away. And so what's going to happen is some of these negative charges are going to move. Not necessarily all of them, not every single one. It's going to depend on the charges of the two objects. But what's going to happen is the objects are going to move so that the electrons are going to have migrated away from the sphere. So that leaves the sphere with a net positive charge. The rod also has a net positive charge, but it's not as positive as it was because it has these extra electrons here, which they aren't showing anymore, but you can see that they're showing fewer positives than there were before because some of those positives are now being canceled out by the electrons that were added. Now, because these are two different sized objects, they don't end up with the same amount of charge. Charge had to be conserved, so I didn't add or lose electrons. I've just moved the electrons around. I have the same total charge I did at the start as I do at the end, but both objects are now positive. So that's the one thing that will be true. If the two objects have different charges and different sizes at the start, they're going to end with the same total amount of charge. The charges will have redistributed themselves, and even though they won't have the exact same charge, they will both be either positive or negative or neutral. Okay, they both have to have the same type of charge that is at the end. So polarization is going to be something that's going to lead us in towards our third type of charging, which is charging by induction. So what happens is when you have a charged object and you bring it near a neutral insulator, the electrons are going to be attracted or repelled. And we can go back to our little simulation and we can see what happens. So over here we have our charged balloon. We can see that it's obviously attracted to the positively charged sweater. But if I look over on the right, I have a neutrally charged wall. Well, we know that opposites attract and that like charges repel. But what happens if you have a neutral object in there? Well, what happens is it always results in attraction. So if I bring the balloon over closer to the wall, I can see, oops, sweater's too strong over there. I'm gonna get a little closer. I can see that the balloon becomes attracted. And if you've ever done this, rubbed a balloon on your sweater and try to stick it to the wall, or sometimes I've seen it done with styrofoam plates. Styrofoam plates work pretty well. The balloon will stick. The wall is still neutral. As you can see, if you were to count the electrons over on the wall, the total amount of electrons and protons has stayed the same in the wall. There's been no transfer, and I can rub on the wall here with the balloon, and there's not going to be any sort of transfer of electrons. So there's no charging by friction. The wall is still neutral, but you can see that as I bring the negatively charged balloon near the wall, that the negative charges get repelled. Now, notice that those positive charges stay in place, and that's important because remember, the protons are stuck in the nucleus, in the atomic structure of the material. The material would completely fall apart if the positive charges just decided to move away. So those positive charges, the nucleus of those atoms, are kind of staying in place, but the electrons are free to move. So they're getting repelled. So what's happening is that's leaving the left side of the wall partially positive and the right side of the wall partially negative. It's temporary. It's creating a temporary dipole. A dipole, that was a word that you might have heard in chemistry. So di meaning two, so two poles, a positive side and a negative side. My charge is still neutral, but I can temporarily create a separation of charge that allows my negatively charged balloon to attract to a neutral wall. So the idea with polarization is when the charge splits. You can kind of see this is a screenshot here with that. We have kind of, I draw a line here, I can see that this side is more partially positive. That's a lowercase delta. They use that in chemistry. Kind of like an unfinished 8. And then this side over here is partially negative. So those are temporary charges. The total charge is still 0. But I've created that polarization. So this is actually how water molecules are. So water molecules are made out of an oxygen with 2 hydrogens, but the atomic structure is set up so that essentially the excess electrons end up unequally distributed in the water molecule. So that if you were to draw a line, the oxygen atom ends partially negative and the hydrogens end up partially positive. And so that creates a dipole. Fun little experiment. You can try this yourself or look up a YouTube video with it. It's pretty fun. But take a rubber balloon, charge it up, rubbing it on like wool. Wool is a really good material for that, polyester. And then have a small stream of water. And that water, you know, out of that fountain is going to come straight down. But if you bring the water towards it, if you can get that balloon charged up really good, you will see that the water stream is actually going to bend towards the balloon, because our balloon has a net negative charge on it when it gets rubbed up against something. And then what happens is these little water molecules are going to rotate so that the hydrogen sides of the water molecules are going to be attracted to the positive sides. And so they're going to rotate. Those positives are going to be attracted to the negative. And all of your little water molecules are going to line up and kind of rotate in space until you create an attractive force. And then that water stream will bend towards the balloon. A fun little experiment you can try at home. So this brings us to charging by induction. So picture what we're starting with. We are starting with this guy right here. So this guy has an insulating stand. So this is like glass or plastic or something. And then you have a conducting sphere. So you have a conductor up here. So the point of the insulator down at the bottom is to isolate it from the ground so that the charges can't move towards the ground. Now, although they're not showing it, this object is going to start with an equal number of positives and negatives. They're not like sitting there like that. I mean, the positives are going to rearrange them, are going to be, the atomic structure is going to be nicely organized for a metal. But then those electrons are actually moving around. So now what happens is if you bring a negative charge over, and I really hate this image, so I'm going to kind of color it in here for a sec, because it's very misleading. All right, so here's our conducting sphere right here. So what happens is if you bring that negative charge over, what ends up happening is it's going to repel the negatives. So the negatives are going to get repelled over to the other side. But those positive charges, they get left behind. So the positive charges don't actually move. That's why I don't really like some of these physics drawings, because they're not really showing what's happening. They're just giving you kind of a representation. So then what happens is, if you draw a line through the center, the side that is closest to the negative rod now has that partial positive charge. And the side that is furthest, that has those extra electrons, is now partially negative. Now this is temporary. If I was to remove the rod, the charges would go back to where they were. So at this stage, we just have polarization. So how do we actually get those charges to move and to stick? Well, what we do is we connect a wire. So they're showing like a copper wire right here. And, And so that copper wire, we often call it a grounding wire because it's connecting to the ground. It doesn't have to be the ground, it could be a table or something. But the idea is that our ground starts off neutral. So our ground starts off with some positive charges And it starts off with we have some negative charges, and it's neutral. So what happens is these electrons over here are all crowded together. They're being repelled closely together. That creates a lot of potential energy. It creates a lot of repulsion forces over on that side. So by connecting the wire, that wire then provides a conduit for those electrons to spread out and get more space. So the negatives are going to move towards this neutral ground right here. Not because the ground was positively charged, but because it's neutral and has a lower density of electrons, so that there's going to be less repulsion. It's not necessarily going to move every single electron, even though that's kind of what this is showing, but you're going to end up with more electrons leaving than what are going to stay and what you had to begin with. So if you were to remove this rod right now, with the wire still attached, what would happen is the repulsion would disappear because we are left with a positively charged sphere at this instant. So if I remove that rod, those electrons that are now extra built up in the ground would want to go back up. So order matters here. So you cannot remove the rod yet. What you have to do is you first have to remove the grounding wire. So what you're going to do then is your ground is going to be left with a net negative charge, and that net positive charge is going to be left up above. Now, once again, I don't like how they've drawn this. They've drawn it with the positive charges on the side. Remember that the positive charges don't move. But what they are trying to represent is that there will be an imbalance of electrons. So really, if you picture about what's going on here, is that you're still going to have your positive charges in their original location, but there are going to be electrons that would have still have been built up over on the side that as soon as you move it, they're going to move and adjust. And so the electrons inside that are left are going to move and adjust until it returns to this evenly balanced state. So a little misleading on these images, but the protons never move. The electrons are going to move and redistribute themselves until the net charge everywhere is the same. Now this can also be done in an opposite way. If I was to have brought a positively charged rod over, then what would happen is the negatives would be attracted. Now let me actually clear this for a sec. So if this was to be So if I was to bring a positive rod over here, what would happen is the electrons would be attracted to the positive rod. So then what happens is you're left with a net positive charge on one side and a net negative charge on the other side. So that if you bring that grounding rod in, that positive that's going to be left over there on the right with the more exposed protons is going to attract more electrons towards the conducting sphere. And then if you remove the rod, the wire, and then remove the rod, what would end up in that case is you would end up with an excess of electrons. And so you could actually get this conducting sphere to have a net negative charge. But the process is the same, except for you'd have to bring a positively charged rod over. So these types of questions make really, really good concept questions because the order matters, what type of charge rod you bring in, and then what's actually going, what's moving. And the most important thing is it's the electrons that move. At no point do the positive charges ever move in this situation. So, how do we know that this is happening? And how did we know about this long before we were able to look inside the atom and see the electrons? Well, someone developed something called an electroscope, and there's different versions of electroscopes. The idea is that you need some lightweight, easy to move metal. Okay, in this case, they're using gold leaves. This is a gold leaf electroscope. It doesn't have to be metal. I've actually had a project where students have made electroscopes You can just use aluminum foil for that. You've got some sort of insulator here that is protecting kind of a metal wire conductor that is coming up through the center. So those leaves are connected to that. And then you've got this conducting metal on the outside. There's also a metal insulator around that's kind of to keep other things from affecting it. So what happens is these two leaves, if there's no charge around, would just hang straight down. And they would hang straight down because they would have equal numbers of positive and negative charges. So you've got your positives kind of equally throughout everywhere, but then they also have the negatives. And so what happens is if you were to say bring a, let's say a positively charged rod over, kind of like what we saw with the induction, because this also works based on kind of polarization, is that you're going to end up with negative charges moving up. So you're going to move up. Not every negative charge is necessarily going to move, but you're going to end up with a collection of negative charges on the kind of top of the metal right up there. Well, what ends up happening is you can see that down lower, we have now created a net positive charge on each of the leaves. So because each leaf is now net positive, and this needs to be kind of set up symmetrically, those leaves will now repel, and what happens is the leaves will separate. And so as those leaves move and separate, that tells us that that rod came towards it was charged. Now, it didn't tell me it's a positive charge. It just tells me that it's charged. Now, I could then ground this with a conductor. So I could ground this, and then what would happen is those negative electrons would then escape. And then I'd have fewer electrons. And now, if I was to remove this rod, what would happen is the electrons would redistribute themselves. So that you have basically the whole thing now has a net positive charge. So my leaves would stay separated because the leaves still have a positive charge on them. Now, what about if I bring another charged object nearby? So let's say I bring a negatively charged object. Well, a negatively charged object would repel those charges, any electrons. Like I said, I'm not showing every charge here on this. I can't do that. There's so many of them. So any negatives that I have up are going to get repelled down. So we're going to add negative charges to the leaves. That's going to cause the leaves to fall back down. So once my positively charged electroscope is exposed to a negative charge, the leaves are going to fall because they're going to be less repelling than they were before. Now, if I was to bring a positively charged rod over here, the positive charges would have attracted more of the electrons that were there away from the leaves, and that would cause the leaves to separate even further because they would be more positively charged than they were before. So there's lots of different things that we can learn and discover with an electroscope. So we could use that by induction, or you could actually charge up the electroscope with conduction. So if you bring a conducting rod, and you actually touch it, then when you touch it, you can actually then provide a positive charge because the electrons would leave. Once again, the electrons would leave, leaving the positive charge with less positive than it had before because some of those positives would be neutralized. So you do have to be careful. Once again, this looks kind of like positive charges are being deposited onto the device. That's not true. What's happening is those electrons that would have been attracted to the positive are getting transferred. So we're canceling out some of these positive charges that were on it. So then if you were to remove this rod and take it away, our electroscope would have a net positive charge because the electrons were transferred to the conducting rod. And remember that conduction can only happen with conductors. An induction requires just doesn't require contact, and it could be with either conductors or insulators. And then the charging by friction requires insulators. So another thing that's different between the insulators and conductors, besides how they become charged, is going to be the distribution of charge. So we have to remember that insulators are going to resist the motion of electrons based on their atomic structure. So for example, if you rub a balloon on your head or on a wool sweater, because that balloon is rubber and it's an insulator, if the electrons that you put on are going to basically stay there. Whereas if you have a conductor and you use some sort of method to transfer those electrons onto the conductor, like conduction, then what's going to happen is those electrons are free to move. So if I put excess electrons on and I put them on over here, they're going to repel each other, and they're going to repel and repel and repel until the electrons are equally distributed among that surface, especially if it's symmetrical. And although it kind of shows the electrons here, they're going to basically be on the outermost edge. Okay, they're going to be on the outermost edge of the device. They can't actually be outside because the electrons are part of the atoms, but picture them on the outermost edge of the surface. They're going to distribute them entirely over that surface until basically the net force on inside is zero, and that all those electrons are basically in equilibrium, because equilibrium, remember, means no net force, which means the electrons are no longer moving. Now, if it's a nice symmetrical object, then the charges are going to distribute themselves equally. So once again, this is a positively charged object, not because we've gained protons, but because we've lost electrons. And because it's symmetrical, they're going to be evenly spaced. Now, if we take a square and we charge up a conducting square or cube or something, they're not going to be equally spaced. Because basically what we want is we want the electric field inside to be zero. We haven't really talked about the electric field, but it's going to be related kind of like to those repulsive forces. And so basically what we want is at the very, very center, we don't want there to be any net force at the center. So that means that our forces, which, think about it, our charges are going to be more repulsive or attractive if they're closer together. If I just look at distance, the sides are closer than the edges, than those corners. So because the corners are further away, in order to cancel out, they're going to need more charge built up. Whereas the portions that are a little bit closer to the center are going to need less charge in order to make those forces cancel, so that electric field is going to be zero. So what ends up happening is our charges tend to build up on like the outermost edges of our object. Think about your fingers. Have you ever walked outside on a dry day or been walking on the carpet and gotten shocked when you touched a doorknob or your car? Well, where are your outermost extremities? Oh, those are your fingers. Okay, so your fingers are going to end up building up the excess charge that when you go to reach and touch something, that's where that shock is going to occur. So, static discharge is going to be when those electrons actually jump through space and transfer onto another object. Have you ever played with one of these little guys, little static balls? They've got this charge, then if you touch it, where you move your fingers is going to change the distribution of kind of those electric rays. And if you've ever I've got this old kind of weird synthetic material blanket that always builds up static charge in winter, especially when it's a really dry day. And man, if I had those lights off and it was pitch black in my room and I could hear and feel that static charge, you could also see it. You could actually see the little sparks of when that static discharge happened. So we can look here at John voltage and see what's going on. All right, so here we have John voltage, and he's walking on this carpet here. And so we can see that as he walks, even though he's wearing insulating shoes, he's actually charging up his body, and the outside of his body by friction. So this is charging by friction right here. Now those electrons are going to repel each other. They don't move very quickly because your clothing tends to be an insulator, but your body is an electrical conductor. Okay, that's actually how the nerves work, we conduct electricity. So I can see that as I build up more and more charge, those charges move and distribute. But if I take John Travolta's hand right here, because he wants to go open that door, he is providing a pathway so that those electrons that are built up to go towards a conductor, okay? And that is that electric shock that you feel when you touch the door. Is actually a transfer of electrons from one object to another, even without actually touching the doorknob. So that charge transfer is going to occur at the point on the object with the highest charge density. So that is going to tend to be at those extremities where we saw. So I hope you have enjoyed a little foray into the basics of electric charge and how we charge up objects. Our next topic is going to be how do we calculate the electric force, that force of repulsion or attraction.